Good day everyone. In this video, we will be tackling about the Programmable Logic Controllers or the PLC. We will discuss what is a PLC, how it works, its main components, how it is programmed, and where it is used in industrial settings. So what is a PLC? A PLC is a specialized industrial computer designed to control machines and processes. Unlike regular computers, PLCs are built to survive harsh environments like heat, vibration, and electrical noise. PLCs replace traditional relay-based control systems because they are more flexible, easier to modify, and more reliable in industrial settings. The PLC purpose. The main purpose of a PLC is to automate industrial operations. It receives input signals from sensors, processes the logic programmed by humans, and sends output signals to actuators like motors and lights. This allows machines to run safely, accurately, and consistently without constant human interventions. Basic components of a PLC. A PLC has several major parts. First, we have the CPU, which acts as the brain and processes all the instructions. Next is the power supply, which provides stable voltage. Then we have the memory, where the program and data are stored. It also includes input modules, which read signals from sensors, and output modules, which controls devices such as motors and relays. So how does a PLC works? A PLC follows a continuous cycle called the scan cycle. First, it reads all the input signals. Then, it executes the user program line by line. After that, it updates the outputs based on the program result. And this cycle repeats in just milliseconds, making PLCs extremely fast.
Now we're going to tackle the PLC programming languages, and the first one is the ladder diagram. The ladder diagram is a graphical programming language for PLCs that resembles electrical relay logic using ranks of contacts and coils to represent control circuits. So we have an example here of the start stop motor control. This where start is normally open, the stop is normally closed, and the motor uses self-hold latching contact. So next is the function block diagram. The function block diagram is a graphical language using blocks to represent functions and their connections. Each block performs a specific operation. Example, the AND or timer. And here's an example of a AND logic with two inputs controlling an output, where input A and input B are being ANDed together to create an output.
Structured text. This is a high-level text-based language. It looks similar to normal programming languages like Pascal or C. It is good for complex math logic and loops. The example shows an if-then rule to turn a motor on or off. Next is instruction list. This is a low-level language that works like assembly code. It runs instructions one at a time, step by step. The example shows loading inputs and controlling an output using short commands like LD and out. Sequential function chart. This is a graphical method. It shows steps, transitions, and actions in order. It is helpful for processes that must follow a sequence. The example shows steps for starting a conveyor, waiting for a sensor, and then stopping it.
Types of Programmable Logic Controllers (PLCs). PLCs come in different forms, and each design suits specific industrial needs. From small machines to large processing systems. Understanding these types helps in choosing the right PLC for a particular application. Let's start with a compact or fixed PLC. The compact or fixed PLC has its components, CPU, power supply, and input-output built into a single unit, featuring a limited number of input-output that is not easily expandable. This setup keeps the PLC simple and practical for small automation tasks that do not require future expansion, making it commonly used in small conveyor systems, vending machines, and basic packaging equipment, where the operations are straightforward and only a few inputs and outputs are needed. For example, a small bakery automating a dough feeding conveyor only needs a sensor to detect dough and a motor to move it forward. So a compact PLC fits perfectly since the process will not require additional sensors or future expansion. The fixed setup keeps the system efficient and cost friendly. Next is modular PLC. In contrast, the modular PLC has components that are separate and can be added or replaced, making the system highly flexible and expandable. The CPU, power supply, and input-output modules are arranged individually, allowing the PLC to grow or be adjusted based on the needs of the process. This design works well for a larger applications such as automobile assembly lines, complex bottling operations, and multi-stage material handling systems, where process may expand over time or require specialized modules supporting long-term customization and upgrades. A practical scenario would be an automobile manufacturing plant, where at first the factory might only automate the welding section using a fewer modules. Later, as robotic painting, inspection systems, or additional assembly stages are added, more modules can simply be attached to the same PLC, making this ability to expand without replacing the entire system, ideal for growing operations. Then we have the rack-mounted PLC. The rack-mounted PLC involves modules mounted on a rack chassis, with each module serving as a specific function. The rack structure organizes the system efficiently and supports a large number of modules working together. This type is used in heavy continuous operations such as water treatment plants, oil or gas refineries, and chemical processing systems, where high reliability and advanced control are necessary. A real-world example is a large water treatment facility, where different stages filtration, chemical dosing, pumping, and flow monitoring require many sensors and actuators running at the same time. A rack-mounted PLC allows all these modules to be arranged neatly in one chassis, providing strong performance and easy maintenance, which is essential for managing complex 24/7 continuous process.
When we talk about automation, we must talk about safety. The safety PLC is not just a regular PLC. It's a specialized device that is certified to meet standards like safety integrity level or performance level. Its job is simple: fail safe. It constantly monitors critical functions like an emergency stop button or a safety light curtain. If an operator steps into a restricted area or a sensor detects a catastrophic failure, the safety PLC's only function is to trigger an immediate protective shutdown of the machine or robot. It is the absolute last line of defense for people and equipment. Moving from safety to scale, how do we run control across massive industrial sites? We use the distributed and network PLC. These systems link multiple PLCs together over a network, sharing data and control of functions across huge distances. This allows us to manage complex environments like large chemical plants or mile-long smart factories, ensuring reliability and efficiency across the whole operation. So, where do these heroes of industry actually work? They are everywhere. They run the packaging and bottling machines that fill millions of products every day with extreme precision and speed. They control sophisticated logistics of a conveyor belt system, deciding in milliseconds where every package or product needs to go. They even manage our cities, running complex traffic light systems that use sensors to dynamically adjust timing for traffic flow and safety. And finally, they are the brain behind the automation revolution, giving precise instructions to robotic arms and manufacturing lines, making mass production possible. The PLC is the foundational technology of the modern world. It is the reliable, split-second decision maker that ensures efficiency, precision, and most importantly, safety in everything we build and everything we use. Thank you. Kapon ka.